So again, just sorry to repeat that. So it's 10 choose 0, 15 choose all 5 marbles, and then 25 total choose 5, right? And of course, as usual, this is not going to be a very high number. If we look at our calculations here, if we set S to 0, again, none of the marbles are red, all the marbles are blue, right? So 15 choose 5, and we arrive at 5%, right? So 0.0565. We're going to do with 1 red marble now, so we'll change S to be 1. 10 choose 1, 25 choose 4, and 25 choose 5 along the bottom. Not 25, sorry, 15 choose 4, and 25 choose 5 on the bottom. So we multiply the top two, we divide by the bottom one, and we get 0.2569. Again, so no more than 2, right, means we either got 0, 1, or 2. So it's not a complement question, right? We're just going to add them all up. And let's just quickly do that now. So 0.0565 plus 0.2569 plus 0.3854. And we get 6988. So the probability that x is less than 3 is equal to 0.6988. And again, just as a quick check for that, let's go over to our distribution question. So this is the histogram with the number of red marbles now. And if we add up 0, 1, and 2, we arrive at 6988, right? So this is our expected number. Again, red marbles, 0 is not that unlikely, 1 is fairly likely, 2 is fairly likely, 5 is very unlikely, right? Because of course that would mean we got no blues, and there are more blues than reds, so it's likely we'll get you know, some blues. Okay, at least 2 red. That means we get 2 red, or 3 red, 4 red, or 5 red, right? So we'd have to add up all of those options. Better option would be to go 1 minus p x equals 0 minus p x equals 1. This way, I'll take all the options, I'll subtract the ones where we got no red, I'll subtract the ones where we got 1 red. So this, we've already done this work, so we're just going to go 0 minus 565 minus 0.2569, right? Using the complement here, at least 2 red means I'm getting 2, 3, 4, 5. Well, let's just do the reverse and take away the options where we get 0 or 1. Again, we can go 1 minus 0.0565 minus 0.2569, and we get 0.6866. Okay, so the probability that x is greater than 1 is 68.66%, right? So it's quite likely. And again, that's reinforced by the view of the histogram. Most of the data is you know, 2, 3, 4, or 5. And again, if we just add up all these numbers, we get 6866, right? Which is where we're getting our value from here. How many red marbles should you expect to select? Okay, well, looking at our histogram, I would guess that this number should be 2, right? It looks like it's fairly symmetrical around 2. Maybe there's a bit more on the left side than there is on the right side visually, so maybe our expected value is a little bit less than 2, maybe 1.9 or something like that might be what we'd expect. But in any case, it would be pretty close to 2 if not. Let's run through the calculation again. So remember, the expected value for any distribution of this type, right, is our r times a divided by n. I'm just going to use the quick way to do this because, you know, on my sheet here, I did do all the xpx's, and we can add them all up. And actually, I see here the answer is actually going to be 2. But let's go through it this way, because this is the way that you should be doing it on your test. I don't want you to be making these tables. It's too much work. It takes too much time. So R, remember, was the number of things we're picking, which is 5. A is the number of things we want, which is 10. the number of successes, good things, desirable things. And then we had 20 was our 25 rather was our total number of things to choose from total. That's 50 divided by 25, which is 2. So we expect to draw 2 red marbles. Okay, that completes that that question. Okay, again, fairly straightforward, I think. But you're gonna need some practice with these just to refresh yourself back from earlier in the course. Okay, let's take a look at this last one. So this last one is just a communication question. We don't actually have to calculate anything. We just want to reinforce some ideas about definitions. Consider the question. At Bill's Burger Barn, there is a 1 in 8 chance of winning a free hamburger. I'm going to go ahead and assume that means when you buy one. Nicholas bought a hamburger every day for 5 days, hoping to win as many free hamburgers as possible. Is this a hypergeometric or a binomial distribution? How do we tell the difference? This is the challenge, of course, on your test, right? Is you just get the question. You don't get what distribution you're supposed to use. So how do you know which one of these things to use? We're going to use hypergeometric if the events are dependent. We're going to use binomial if the events are independent. Now, based on this question, it seems the way I read it is every time you buy a hamburger, you have a 1 in 8 chance of getting a free one. To me, I read that as an independent event. Every time I buy one, I have a 1 in 8 chance. It doesn't matter if I've already won or if I haven't won. The point is, it's a 1 in 8 chance every time. This leads me to believe this would be, I would use the binomial distribution to solve this problem because the events are independent. Each hamburger has no bearing on whether the next one is free or not. P equals 1/8 always. If we were going to solve this question, well, he buys 5 hamburgers, so n is 5. X, it would be the number of successes. So it could be 0, 1, 2, 3, 4, or 5. P is 1/8 and Q is 7/8. And we would just use this in our binomial formula, right, from the other day. Remember, it's it's NCX times P to the X times Q to the N minus X. Okay, and we would just use that formula to work out the probability of getting, 1 hamburger, 2 hamburgers, 3 hamburgers free, and so on. How many free ones did he get? We could calculate EX very quickly. It's just equal to NP, which is equal to 5 times 1/8, which is equal to 6125, hopefully. That means he should expect to have won 0.6 free hamburgers by the time he's done his 5. He's bought 5 of them, every hamburger one for 5 days, right? Okay, so really this question was just asking us, is it hypergeometric or is it binomial? My interpretation of this question is every time I buy the hamburger, my chance is 1/8 that it will be free. Because that has nothing to do with whether I have bought any hamburgers in the past, this is an independent trial, right? Each time I do it, it has a chance that doesn't change. Now, rewrite the question so as to convert it into the distribution not chosen in A. Okay, so if we are going to rewrite this question to be a hypergeometric, we have to change the conditions of the deal such that every time you buy a hamburger, your probability of winning changes. Okay, and that's the main difference. Now, you might think to yourself for a second, or talk to the person beside you, how would we make this contest change so that every time I bought one, my chances of getting my next one would be different? Okay, and I think the way that we could do that, which again is not quite ideal in this question, but the way I'm thinking of doing that is let's change the conditions of the question. So what we need to do here is we need to define a number of free hamburgers and define a number of sales, so that basically every time he sells one, the probability would change. So, okay, so before it was a 1 out of 8 thing, so let's keep that consistent. So let's change the question to Bill, in the next 1,000 hamburgers he sells, Bill is going to give away what would be 1 out of 8, there would be 125 free hamburgers. And he will tell, he'll have a sign or something that tells customers how many of each are left. So let's say I walk in on the first day and I'm the first customer, right? A would be my 125. It's 125 free hamburgers. N, it would be 1,000. X would be for me, right? Depending on how many it is that I'm willing to buy, right? Let's maybe set R first as how many I'm willing to buy. It could be 1, right? It could be 2. It could be more than that. And X could be 0 or 1, right? It could raise up the R. And so in this way, let's say 3 days later he only has 30 hamburgers left and only 2 of them are free, right? It could make it a bit easier for our math numbers. And then we could calculate it that way. I wouldn't get too hung up on this. I think the thing to understand here is this, okay? It's hypergeometric if every time you do the experiment, it affects the next trial. So for instance, if I buy this hamburger, that means there's one less hamburger that costs money, and there's one, it's that much more likely that I might get the free one next time, right? It's like what we were doing with Deal or No Deal the other day, where every time you took away a case, it changed the probabilities, right? It affected them. The independent one, which is when we use the binomial, are when there is no change to the probability, no matter how many times you try it. This would be like flipping a coin, right? I flip a coin, doesn't matter if I flip it 1,000 times, 2,000 times, that the probability of getting ahead is always 0.5. It does not change, okay? And that's the number one sort of thinking element, I really want you guys to focus on. I think this question is kind of odd, but the idea it's trying to get at is really important, okay? Dependent versus independent use different formulas. Okay, hypergeometric distributions, you've done them before. You've done this combination work before. This is not new. We're just using some new language to describe it. The thing that we need to understand with these is that the probability of success changes from trial to trial. If you try to put this into a binomial, it will not make sense, because every time you do the experiment, the probability changes. Okay, take a few minutes to flip through the learning goals here. Make sure you can assess yourself and see how you're doing. Try some problems today while you have time. And remember that Monday we have the entire class for you to bring any questions to me. Okay, enjoy the rest of your day.